Welcome to the presentation of the paper Compressed SIKE Round 3 on Cortex-M4. My name is Mila Anastasova, and this work has been a collaboration with Mojtaba Bisheh-Niasar, Dr. Reza Azarderakhsh, and Dr. Mehran Kermani. In this presentation, we will go through a brief introduction pointing out the motivation behind the post-quantum cryptography and the timeline of the developed schemes. We will continue talking about the super-singular isogeny key encapsulation mechanism SIKE and its variant compressed SIKE. Then we'll have a look at the target platform of this work and its main characteristics. Later we will discuss the implementation strategies that we have applied and the performance improvements that we have achieved. Finally, we will conclude our work. The nature of quantum computers, in particular their data unit, the qubit, and the principle of superposition, threatens the classical cryptography schemes that are used nowadays, such as RSA and the elliptic curve cryptography family of algorithms. Driven by the increasing capabilities of quantum computers, the National Institute of Standards and Technology NIST has initiated a standardization process where the quantum robust schemes are being evaluated while going through several optimizations. The standardization effort has started in the year 2016, and until the year 2020, 2 rounds of the competition has been completed, announcing several finalist schemes. Round 3 of the competition is expected to finish during this year, where the alternate candidates, along with the finalists, are going through additional optimizations and improvements. The integration of the post-quantum cryptography into the SSL and the TLS communication protocols is expected to be completed no later than the year 2035, when a powerful quantum computer is expected to be developed. The super-singular isogeny key encapsulation mechanism is the only isogeny-based primitive in the scope of the post-quantum standardization process. It consists of secret isogeny maps calculated by both communication parties, leading them to curves featuring the same characteristics, which they use to agree on a shared secret for further cheap symmetric communication. The algorithm attracts with the smallest key sizes among the post-quantum algorithms and therefore ensures small communication latency and becomes a good fit in the Internet of Things scenario where the bandwidth is limited. The main drawback of the algorithm, however, is the performance cost, which is significantly higher than other post-quantum candidates due to the complex isogenous computations. This places the algorithm into the alternate candidates during round 3 of the post-quantum standardization process, therefore incites several research groups to focus on optimizing its timing. In 2016, Azarderakhsh and his team proposed even further optimization of the super-singular isogeny key encapsulation mechanism, introducing the compression mechanism, where they decrease the sizes by a factor of 4, the key sizes by a factor of 4. The main idea behind the compression mechanism is to replace the curve points, part of the public key and the ciphertext information, with shorter representation. For this purpose, both parties generate bases R1, R2 and S1, S2, where they use them to describe the points using 4 shorter integers. Further improvements have been suggested later in the literature, where only 3 variables are used, representing linear combination of the previous 4 variables. This algorithm, however, introduces a significant timing overhead to the SIKE algorithm. However, due to the extremely small key sizes and ciphertext sizes, it continues to incite researchers to work on improving the performance of the compressed SIKE protocol. The target platform in the scope of this work is the Cortex-M4 processor. We have used the board STM32F407VG, the discovery board, recommended by NIST for targeting and benchmarking the post-quantum algorithms. This platform is based on ARM v7M architecture and features 16 32-bit general-purpose or core registers where only 14 of them are available to the programmer, and another 32-bit floating point registers where all of them can be modified by the user. The simplicity of the architecture ensures a single clock cycle per instruction, with the exception of the memory access instructions, which add an extra clock cycle for their completion. Taking into consideration the design of the platform, the main challenges when implementing long integer arithmetic operations based off SIKE and compressed SIKE is to efficiently use the minimal register set offered by the target in order to decrease the memory accesses as much as possible and to propagate correctly the carry or borrow information through the words of the operands. In this work, we have focused on the low-level arithmetic operations, where due to the pyramid-like structure of SIKE and compressed SIKE, they ensure overall speed up of the algorithm. Our main implementation strategies are the integration of the entire register set, including the use of floating point registers as a cache memory level 1, which ensures instant data access and thus reduces the clock cycles required for memory accesses. We have also rearranged the instruction flow to increase the size of the operation block, thus to schedule the inevitable memory accesses and reduce the execution latency. Continuing to talk about our target board, we should mention that it features 1 MB of flash memory and another 192 KB of RAM. However, as we can see on the memory map of the device, the RAM is split into two different regions, 128 KB of SRAM and another 64 KB of CCM RAM. For efficiency purposes, the PQM4 library, base of our benchmarking, integrates only the first 112 KB of the SRAM memory, marked in red in our figure. We have observed that this space is not enough for the execution of compressed SIKE P610 due to the large local data structures which reside into the stack. Thus, we have increased the size of the stack, adding the additional 16 KB of the SRAM region marked in green on our picture. However, even the entire set of 128 KB of SRAM was not enough for the execution of compressed SIKE P610 without corrupting the memory. Therefore, we have created a new memory region into the CCM RAM memory, where we placed part of the large data structures. We had to slightly modify the code to address correctly the different parts of the split data structures. The entire set of 192 KB, however, was not enough to fit compressed SIKE P751, therefore it is not focus of this work. For the performance optimizations that we report at the end of the presentation, we have implemented subroutines that are particular for compressed SIKE in assembly code. The first finite field operation focus of this work is the modular subtraction with correction 2p or 4p, where for simplicity we represent both values on the slides as capital letter P. To speed up the execution of the operation, we have integrated the strategies proposed earlier in the literature. We have increased the size of the operation block from 4 to 5 limbs per operation block, which allows better scheduling of the instructions, therefore less memory access stalls, ensuring consecutive memory accesses, which allow the stall cycles to be absorbed by the following instruction. Another technique that we have implemented is the operation block alternation. As we can see on the figure, the sub and add operation blocks are alternating, allowing the propagation of the carry or borrow flag without the need of carry or borrow catcher or activator. Therefore, we use less instructions for the implementation of the subroutine. We also use reduced instruction set for the implementation of the carry or borrow, catcher or activator. In more details, for the carry or borrow catcher, we subtract the assigned carry or borrow catcher register from itself with the carry flag activated, where we use the same register to store the resulting value. In case the flag is active, the resulting value will be equal to -1 or to FFF in hexadecimal representation. Otherwise, the register will be equal to 0. For the carry or borrow activator, we use the reverse subtraction instruction, where we subtract the carry or borrow catcher register from 0. If the catcher register was equal to 0, the carry flag will be disabled. Otherwise, it will be set to 1, and the carry or borrow can be propagated to the following operational blocks. The second arithmetic operation that we have implemented is the multi-precision multiplication. Due to the shorter form of the public key and the ciphertext representations, where they are represented with the help of several variables of short length, the need of multi-precision multiplication of different sizes than the finite field is required. In the case of SIKE P434 and P503, a multiplication of 256 by 256 bits is needed, and in the case of SIKE P610, a multiplication of 320 by 320 bits is required. We implement these subroutines using the refined operand caching technique, where we keep the row sizes equal to 4, as we can see on the figure. We also integrate the use of floating point registers, as suggested previously in the literature, to obtain maximum speed of the multi-precision multiplication by reducing the memory accesses significantly. As we can see again on our figure, we do that by keeping our partial results, the results that we obtain in between the rows, we keep these values inside our floating point register set. In this way, using the vmove instruction, we can transfer the values between the R and S registers, and therefore we can obtain our data instantly, eliminating the memory access stalls. These subroutines have not been previously implemented in assembly language, thus we could only perform our comparison with the C code provided in the PQCrypto SIDH library. The comparison table shows that the target-specific implementation of the subtraction and the multiplication improved by 76 and 95% respectively for P434, 77 and 95% for P503, and 77 and 96% for P610. This data, as shown on the table, shows around 76% of improvement in the execution time of the subtraction and around 96% of improvement for multi-precision multiplication subroutine for all the security levels. Not only the implementation of the particular compressed SIKE subroutine or subroutines affect the performance of the entire protocol, but also the high invocation rate of this operation contributes to the significant effect of these target-specific implementations. We report our results running the protocol at 24 MHz, which ensures zero wait state and allows precise measurement of the protocol. This measurement is shown on the left-hand side of our slide. We report the total execution time as the sum of encapsulation and decapsulation. For the integration of the protocol into a real scenario, we report a timing in seconds, where we run the compressed SIKE at the maximum speed offered by the target device, which is at 168 MHz. We report these results on the right-hand side of our slide, and we also see the timing measured in seconds. Even though we propose the first integration into compressed SIKE into low-end devices with such limited resources, we integrate the previous best reported implementation strategies on the standard SIKE into the compressed SIKE implementation for comparison purposes. We observe that our code reaches up to 25% of improvement for security level 1 of the protocol, comparing our work with the work of Seo et al. And his team, and 16% of improvement comparing with the work presented by Anastasova and her team. For security level 2, we obtained 21 and 13% of improvement, as we can see marked in green, and for the security level 3, we obtained 20 and 13% of improvement respectively. Our implementation design allows the execution of the algorithm in 1.26 seconds for security level 1, 1.89 seconds for security level 2, and 3.36 seconds for security level 3, which, as it can be seen on the table, represents significant improvement of the timing of the algorithm. In the following table, we can observe the comparison between compressed SIKE with the finalists and the alternate post-quantum candidates. We can see marked in red the timing overhead of compressed SIKE compared to standard SIKE, and in green the communicated data overhead when uncompressed SIKE is being executed. The table shows clearly the advantages and disadvantages of the post-quantum candidates, where it can be seen that the timing of SIKE and compressed SIKE forms their main drawback. However, in scenarios of limited bandwidth, where the communication introduces huge latency, the use of isogeny-based schemes comes into use. Concluding our work, we have proposed the first integration of compressed SIKE security level 1, 2, and 3 into low-end embedded systems with limited resources. We have increased the size of the stack and created a new memory region into the CCM RAM to split large data structures, eliminating memory corruption and allowing the execution of SIKE P610 on the target device. We have integrated the previous best reported work on SIKE into the compressed SIKE and observed up to 16% of performance improvement after the implementation of the compressed SIKE specific subroutines in assembly language. Thank you very much for your attention. For any questions that you may have, please don't hesitate to contact us via email. Thank you.